We are going to conduct a clinical post-mortem on the structural and hydrodynamic failure of a 52,000-ton vessel. The RMS Titanic relied on the primary defense mechanism against catastrophic flooding, a system we can call the buoyancy matrix. The lower hull was subdivided into 16 distinct watertight compartments, separated by heavy steel walls known as transverse bulkheads. The baseline operational tolerance was robust. The ship could maintain stability with any 2 compartments completely flooded. The maximum engineered survival threshold was even higher. The system was designed to remain buoyant even if the first 4 forward compartments were simultaneously breached and flooded. But this system had a strict mathematical boundary. Breaching 5 or more compartments would guarantee a total loss of buoyancy. Under any standard operational damage profile, this internal architecture rendered the vessel mathematically unsinkable. To understand why this system failed, we must look at the specific environmental parameters operating on the night of April 14, 1912. The first critical variable was the thermal state of the environment. The temperature of the seawater had dropped to -2 degrees Celsius. The second set of variables was kinetic. Prior to impact, the vessel had a displacement mass of 52,310 tons, moving at a velocity of 22.5 knots. Calculating these figures yields the total kinetic energy of the system entering the collision event, roughly 3.56 gigajoules. This massive forward energy was directed at an immovable target, a land-based glacial ice mass with an estimated mass of over 1 million tons. When a moving object strikes an immovable one, the laws of physics dictate a strict consequence. The ship's architecture is forced to dissipate 100% of that kinetic energy internally. The impending collision was a maximum stress kinetic shear test, one that pushed the structural steel far beyond the material limits of the era. The collision was not a direct head-on impact. It was a glancing, high-pressure scrape along the starboard side of the hull. The hull plates taking this pressure were manufactured using the open hearth process. While an advancement for its time, forensic analysis reveals this steel contained elevated concentrations of phosphorus and sulfur. These impurities severely affect a material property known as the ductile to brittle transition temperature, or DBTT. This is the thermal threshold where a metal loses its ability to deform plastically and absorb energy, and instead fractures. Modern testing of recovered hull plates revealed a severe anomaly. The ship's steel transitioned into a brittle state at exceptionally high temperatures, between +40 and +70 degrees Celsius. Compare that transition threshold to the actual service conditions of the vessel. The seawater that night was -2 degrees Celsius. At -2 degrees, the steel possessed virtually no capacity for plastic deformation. This image of a recovered hull plate shows the mechanical result: jagged, sharply fractured edges, completely lacking the deformation characteristics of ductile tearing. Under stress, the steel shattered like glass. The entire outer defense of the buoyancy matrix was thermally compromised by the freezing ocean before the iceberg ever made contact. To find the exact mechanism of the hull's failure, we have to look past the massive steel plates and focus on the microscopic points of failure, the fasteners. Where the bow of the ship tapers sharply, the structural curvature prevented the use of large hydraulic presses. Instead, the shipyard used wrought-iron rivets that could be manually hammered into place. Metallurgical analysis by the National Institute of Standards and Technology discovered a severe microstructural flaw. These specific wrought-iron rivets contained an average of 9.3% iron silicate slag. This concentration of slag is 3 times higher than the specified limit for premium best grade wrought iron of the era. The manual installation process compounded this defect. Hammering the heads flat dangerously reoriented the excessive slag. This horizontal orientation created severe microstructural anisotropy. The dark slag filaments acted as a massive internal notch effect, a pre-existing fracture line built directly into the fastener. When the 3.56 gigajoules of lateral prying force from the iceberg reached these flawed components, the brittle rivet heads instantly sheared off. This triggered a zipper-like cascade. As one rivet failed, its load instantly transferred to the next, causing the hull seams to forcefully unzip along the starboard side. This failure mechanism definitively debunks the historical myth that the iceberg tore a continuous 300-foot gash into the side of the ship. Sonar mapping and forensic modeling revealed the true breach profile: 6 discontinuous, narrow openings along the seams, totaling just 1.17 square meters of compromised area. The macrostructural integrity of a 52,000-ton hull was completely defeated by a localized microstructural defect inside a 1-inch fastener. While 1.17 square meters of damage is remarkably small, its spatial distribution was fatal. The iceberg scraped the hull just long enough to distribute 6 narrow breaches exactly across the first 5 forward compartments. We determined the volume of water entering these breaches using Bernoulli's fluid dynamics equation, factoring in the 25-foot hydrostatic pressure head at the exact depth of the damage. This graph plots flooding over time. At the origin, we see an initial ingress rate of 13.3 tons of seawater per second. As the internal water rises, the pressure differential drops and the inflow decelerates, flattening the curve. But this deceleration was insufficient. The total volume of the 5 breached compartments was simply too large, and the incoming mass too heavy for the system to stabilize. The precise spatial distribution of that tiny 12-square-foot breach had initiated an unstoppable mathematical countdown to total system failure. The buoyancy matrix possessed one final fatal architectural vulnerability. The transverse bulkheads were uncapped. These watertight dividers did not extend all the way up to the main deck. Instead, they terminated prematurely at E deck and D deck. As thousands of tons of seawater accumulated in the 5 forward compartments, the aggregate weight drastically shifted the ship's longitudinal trim angle, pulling the bow deep into the water. This downward pitch induced the ice cube tray effect. The water level reached the top of the divider, aggressively spilling into the adjacent chamber. Hydrostatic pressure continuously forced water over the E-deck bulkheads, progressively flooding the next dry compartment. With each new compartment flooded, the bow pitched further downward, geometrically accelerating the rate of spillover and the total loss of system buoyancy. This shifting trim initiated a secondary structural consequence. As the bow sank, the stern was lifted entirely out of the water, exerting extreme bending moments on the main hull girder. The vessel was subjected to massive hogging and sagging forces. Suspended in the air, the architecture was unsupported. These bending forces multiplied until they catastrophically exceeded the ultimate yield strength of the steel. The system was not destroyed by an iceberg. It collapsed under a cascading intersection of thermal embrittlement, anisotropic rivet failure, and a hydrostatic override that exploited a critical architectural